Last week, we have seen that in a network like this one, being optimally efficient might lead to switching off the red source, for example, that uses many links. And we have introduced the concept of Pareto efficiency by saying that an allocation of links is Pareto efficient if it can be increased unilaterally. And this is one example of one Pareto efficient allocation. We see the rate values are given here. They're repeated at every link for making the thing easier to find. We see that we cannot increase the red here because there is a limit here. The red has a bottleneck. We cannot increase the green because here there is a bottleneck, and here as well. And here another allocation, which is also Pareto efficient for the same reasons. We cannot increase the red or the blue or the green or the black, but the values are different. For example, here, this link is not fully utilized, but still the allocation is Pareto efficient because we cannot increase unilaterally any of the rates. So in some sense, we've reached an extremal point. But the question that this raises is that among all Pareto efficient allocations, what are the ones that we would like to implement? What are the things that we should do on the internet? We've seen that an allocation that is particularly not interesting is the one that gives 0 to this flow here. So what should we do? And the concept that leads us when we say giving 0 to the red flow is not good, it is because it is not fair. So we want to somehow allow everyone to get some share of the resources, even if it's the same for everyone. And what should such a concept be? What is fairness? So that's the topic now of this section. So let's look at this example again. So we have here only 2 links. The red flow has a rate x0. We have those 2 capacities here. I could do this, which gives the same to everyone here. And I could do this, which also gives the same to everyone, but a larger value, or this one here. This is an example of fairness that we could call egalitarianism, which is the principle that says we give the same to everyone. And of course, as much as possible. This is what communists in countries that were communist or pretend to be communist today said they do. They don't do it at all, but that's what the theory said it should be. One of those 2 allocations satisfying this principle here. I'm closing in a few seconds. Closing. And the correct answer is B. That's easy to see by casting this as an optimization program. If we want to give the same to everyone, then let's call X the common value that every flow receives. What are the constraints? Well, this link and this link gives those 2 constraints. And we need to maximize this. Well, if you look at the 2 constraints, we see that one is superseded by the other. So it's X less than or equal to 1. The max of X is 1. So we should give 1 to everyone in this case here. So that is what this dogma would give here. But this, of course, is not so good because it's not Pareto efficient. If we give 1 to everyone here, then the capacity here of this link is not increased. Here, this guy receives 1, this guy receives 1. And the reason of the receiving 1 is because the red and the green exist. But it's not a local constraint on the blue. We could increase the blue by making it 9, for example, and not change the others. So that means this allocation is not Pareto efficient. It's not a good allocation in the minimum sense of efficiency. because I have more to run without hurting any of the others. So there's no reason not to do it. So a better allocation could be this one here. So I give one to the red, one to the green, and by doing that, I discover that there is some free capacity, and I increase the capacity as much as I can. And by doing that, at least intuitively, we can convince ourselves that we're not hurting anybody, so we should do it. In fact, this numerical example is what is called a max-min fair allocation. For this example, if we apply a first concept of fairness, which is called max-min fairness, this is what we would give. So intuitively, this example illustrates what max-min fairness is about. We try to give the same to everyone, but still allowing some to receive more than others if there are local constraints that allow this to happen without hurting the others. The formal definition is this one. That's a definition we are using in the context of rates of TCP connections or flows in the internet, but that's a very general concept in any resource allocation problem. I have a vector X that captures the resources I allocate to each of the sources. Of course, some X are feasible, some not. So the feasibility constraints are, for example, here that the link capacity constraints are satisfied. So among all the feasible allocation, we say that this one is max-min fair if for any other equally feasible allocation, which I call X primes, if the following sentence must be true for any other allocation. If I can find another allocation in which there exists a source that receives more, there must exist another source that receives less. And this source that was receiving less was less rich or the same as the source that has been giving more. In other words, if for every source, increasing its rate must force the rate of some other source which is not richer to decrease here. So it's not the game of Robin Hood. Robin Hood takes from the guys who are rich to give it to the poor, so that is allowed. But if you give to somebody who is poor to increase the rich, you have what is called a liberalism or capitalism. But this is not allowed in the sense of max-min fairness here. So that's the formal definition here. So let's try here on this scenario again. Here I have two allocations. I gave a hint already, but we can verify which, if any, of those allocations happen to be max-min fair. I close the poll in a few seconds. Closing. The majority says B, which in some sense is the only thing that we can say find by guessing, because I mentioned that this is max-min fair. So if you believe me, although you should not always, this is the max-min fair allocation. And this one, well, the motivation that I introduced for introducing the concept of fairness is to avoid that kind of allocation. This is not fair, if I say intuitively. So if my theory of max-min fairness says this is max-min fair, probably I would have a contradiction somewhere. But let's look mathematically how we can apply the definition. The allocation A that gives 0 to this guy, well, let's try to see whether, well, we claim it's not max-min fair, so let's try to increase it without violating the concept that is given. So we increase it in the Robin Hood way. I can increase x0. For example, I can make it 1 by decreasing x1, which is this guy here, by making it 9, and x2 by each of those x's, making them 1 also. So that really is a feasible allocation. And I've increased the value of somebody who was the poorest of all guys, and I'm still feasible. So that means this thing was not max-min fair. I can do better in the sense of fairness than this one, so it's not max-min fair. For this one, if we try to do the same thing, well, let's try. If I increase x0 is 1, x1 is 9, so this link is saturated. If I increase x0, I must decrease x1, but that's okay because x1 was larger. If I look at the second link, we see the second link is also saturated. So if I increase x0, which is 1, I must decrease one of the guys which had the same value. So that violates fairness, so that satisfies the constraint we had before. For any, if I try to increase x0, I must decrease somebody that's not richer. And if we look at all the different cases, it's the same for x1. If I increase x1, I must decrease x0, which is poorer. And if I increase x1 of the x2s here, I must, or x2, let's say they're forced to be the same, I must decrease x1. So any move that I do here contradicts the fairness. So it satisfies the constraint, the statement we made here. For any move that I do, if this move is increasing one of the sources, it always decreases one sources that were less better off. So it is max-min fair. Fortunately, we need to look in practice at such contorted way of checking the definition, because there's a well-known theory of max-min fairness, which is summarized here. Given a set of constraints for the rates, this makes, if we write the constraints for the toy formulation of the problems I have, we obtain a convex problem. And for convex allocation problems, we have the following results. The max-min fair allocation always exists, and it's always unique, whether the problem is convex or not here. So in our network setting, we always have linear inequalities, so we have convex problems. Therefore, there is always a max-min fair allocation, and only one. So back to the quiz of a few minutes ago, it was not possible to have two allocations that are max-min fair at the same time. There's only one. It's unique here. Last, it's always Pareto efficient, but this is obviously true, because if we could increase unilaterally, then we would violate the condition here. But of course, as we have seen, the converse is not true. There are Pareto efficient allocations that are not necessarily the max-min fair allocation. That's about the theory. That's the good news. We can speak of the max-min fair allocation of rates, which is well defined and is unique here. Even better, there is a simple algorithm called water filling algorithm to compute it, which consists in increasing the rates of all sources, starting with the egalitarian principle, give the same rates to all, find the maximum value, so increase all the rates until we cannot increase anymore. That will give us the maximum common value. And then close the sources that obtain binding constraints, so the sources that use a saturated link, and continue increasing the others at the same pace, giving the same rates to others, until all the links, until we have no source that can be increased. So let's try this on this example. I have those set of sources. At step one, I give the same rates to everyone that maximizes this common rate. That's the link that's the exercise we did a few minutes ago. The answer is we give 1 to everyone, 1 to each of the flows. And when we do this, we find that this rate here is saturated. This link is saturated because the constraint, which is that 1 plus 9 is equal to 10. So this is what is often in this context called a bottleneck link. This link is a bottleneck link. And all the sources, all the flows that use the bottleneck link are frozen. They cannot increase. So we fix the values of x0 and x2. We mark them as frozen. And then we continue. Now we have a free variable, which is x1. We increase it as much as possible until we hit the limit, and we find the value of 9 here. So now link 1 is saturated. It's used by source 1. So source 1 is frozen. All sources are frozen, Therefore, the algorithm stops here. This algorithm will stop always because at every iteration we have at least one source that is frozen, and we can always increase at least one source. So there's a finite number of it will stop at some point here. So that's another way, simpler, to prove that the max-min fair allocation is this one. So let's try this algorithm on this example. Here is a tandem network where you have a long series of links here with short links that come here. This is sometimes called the parking lot scenario in some parking lots like Beaulieu in Lausanne. When you're unlucky and you are this guy, you have to go through all the different What is the maximum fair allocation for this case here? Here I have 4 links and 5 sources. I close the call in a few seconds. Closing now. And the answer here is simple. It is A, and it works in only one step. I try to give a common weight to everyone, and this common weight must satisfy that x plus x is less than c, so 2x is less than c, and the 4 constraints give the same inequality. So the max of x such that 2x is less than c is c over 2. So it gives the same to everyone here. That is the max-min fair allocation. Well, so the max-min fair allocation is used by many settings where we allocate resources, for example, in cellular networks, also in some internet settings here. But this has been criticized by some researchers that said that if we look at a case like this, the red connection receives the same as each of the blue connections, whereas in fact the red connection is using much, much more resources here. So it's not okay to give 0 to the red. We would like the thing to still work, but perhaps we should need a more proportional allocation of resources to the fact that this guy is using 4 links and this one is using 1. So intuitively, for a case like this guy is using 4 times more than this one, so perhaps he should also receive 4 times less in total, because whatever he receives in total is in fact multiplied by 4 in terms of usage of the resources here. This leads to another definition of fairness. So the bad news about fairness is that there are multiple definitions, but those two, proportional and max-min, are really the 2 essential definitions. So let's see what is proportional fairness. It's a bit more complicated to explain, but not so much. So we say that a feasible rate vector x is proportionally fair if for any other feasible allocation, first, it applies only if we can make sure that every source gets at least a positive value, because we have a denominator here. If this thing here is negative or 0, this thing is the rate of change. So it is saying I have 2 allocations, the first and the second. I look at the delta for every source, but I don't look at and I look at the aggregate of the deltas, but not by summing the delta, but by summing delta divided by x, which is the relative change. So this is based on the intuition that what matters in terms of fairness is not so much what value, if you can give 0 to someone who has already 100 or someone who has already 1, I mean, if you give +1 to those 2 sources, the perceived benefits for the second one is huge. You have double the rate of the second one. For the first one, you've increased from 100 to 101. So probably nobody cares about such an increase here. 1% increase is no big deal here. So This is captured by this formula here. We take not the total delta, but the total rate of change. So the rate of change is if I move from one location to another one, we look at the percentage of change for everyone, plus it's a positive or negative number. So if, for example, if I start from a Pareto efficient allocation, and if I deviate from it, I will, because it's Pareto efficient, if I increase some, I will need to decrease some others. Otherwise, it will not be Pareto efficient. So there will be negative changes, negative percentage for some, negative for others, and we do the integral of all this. If the integral of all those changes is negative, then this change should be done. Sorry, if the is positive, then we should be done. If for any application is negative, that means we've reached an extremal point or a fixed point in some sense. We can do better because whenever we do from this allocation, we will increase for some, decrease from others, but in average, the sum of the percentage will be, so the average percentage per flow is negative. So if that happens, then we have what is called a proportionally fair allocation. So this is a bit more complicated to express, but it captures two things. The first thing is that what matters is the sum of all rates of changes, which means that if somebody uses many resources, by decreasing a bit this guy, we can give much more to the others. So we should do it. So that is what is captured here. It is capturing the fact that it is, in some sense, appointing allocation to the use of resources. And the other thing that it captures is that what matters is the relative share, not the absolute value, as I said before. Whether we change from 100 to 101 or 1 to 2 is a big difference, which is not captured by the max-min fair definition here. So same question here. I have this example A, where I propose one allocation, the one we've computed before. That's the max-min fair allocation in this example. And this is also the max-min fair allocation in a second example. Is in any of the cases, the max-min fair allocation also equal to the proportionally fair allocation. Is the poll open for you? No, yeah, I'm suspecting there is a problem. So after a PhD in computer science, you learn one thing, right, which is to stop and restart. Does it look better? Yes, okay. It has to do with distributed systems that are not, and the impossibility of consensus with bounded time, right? So we need. I close the poll in a few seconds. So there is almost a tie between B and D. Well, this is a bit more complicated, so let's look at it in detail. The correct answer is D. None of the two is proportionally fair. Let's look at the first allocation. Here, that was my motivation for proportionally fairness instead of maximum fairness. So we expect it's not proportionally fair, but let's verify it formally. Well, let's try to do a move that will invalidate the fact that this allocation is proportionally fair. And the intuition is the red which gets half of the rate should get less. So let's try to decrease the rate of the red flow by delta, which allows us to increase the rate of the other flows by the same delta. And if delta is small enough, if delta is less than C/2, this is feasible. That's a feasible allocation. Now, what is the total rate of change? Well, for the red one, he has lost delta, and before had C/2. So the relative change is this, minus delta over C/2. For the others, the relative change is the same, but there are 4 of them. So the sum of all the total rate of change is this 4 times. So 4 minus 1, that gives 3 delta over C/2, which is positive. So I can do a change that has a positive total rate of change. Therefore, the allocation is not proportionally fair. We can verify the same thing here. If I decrease x0 by 9 delta, I can give the same delta to each of the green flows. And x1, it can be increased by plus 9 delta. And if we do the total rate of change, it's also positive. Not by much, but it is positive. So none of those 2 allocations are proportionally fair, which leads us to the question, well, can we say something smarter about proportionally fair allocation than this axiomatic definition? And the answer is yes. The proportionally fair allocation, first, like max-min fair, if the set of constraints is convex, which is the case for us in the simple networking models we have, then it always exists and is unique. And the reason it exists and is unique is because it corresponds to maximizing the sum of the log of the rates, logarithm of the rates. You could say log is a weird thing because there's no unit, but if we change the unit, we just add a constant to the log, because log x multiplied by lambda is log x plus log lambda. So in terms of maximization, it's independent of the units here. And the intuitive explanation is if I try to maximize the logarithm, I mean, the log is strictly concave. So it has, if it has a local maximum, it is the global maximum, and it must be unique. That's a property of convex optimization problem. And second, if I try to maximize this, I will move in the direction of the gradient. And the gradient, if I change by a little amount dxi, the value of x, this is the gradient here. So I should move in this direction, which essentially is saying, this is, you recognize here in the limit, something that's close to what I had called the total rate of change. So if I start from an allocation and I try to move towards the maximizing point of this function here, I will try to move to take steps where at every step I increase the total rate of change here. Until I reach a point, I can do this, which means in whatever direction I move away from this, this must be negative. That's one way to view maximum point. Whenever we follow the gradient in any direction here, we have a negative increase, which means we have the maximum. That's not a proof, that's just trying to give the intuition. The consequence of this is that the proportionally fair allocation is Pareto efficient because it's maximizing the positive function of the rates. So if I try to unilaterally increase one of the x, then obviously that would not be the maximum, optimal here. So numerical, it's a bit more complicated. Let's do it for this example here. We have seen that the max-min fair allocation was not proportionally fair. Now, if I want to find the proportionally fair allocation, I have to solve the following optimization problem. Maximize the sum of the rates of those 5 connect, subject to the constraints. Now, the constraints are at every flow like this here. So you recognize here, it's not a linear program, but it's not a bad one. It's a convex program because we're maximizing a concave function. The convex program is maximizing a concave function over a convex set, or minimizing a convex function over a convex set. This is convex because it's all linear inequalities, and this is concave because the log is concave. So we can use convex programming. So MATLAB will do it easily for you. In this toy example here, we can do a direct solution because since we know this, the the solution must be Pareto efficient, then we can easily see that in this special example, there is a free variable at every constraint. So every constraint must be satisfied with equality, because if it's not satisfied with equality, for example, if the first link is not saturated, I can always increase x1. Right. So since the proportionally fair allocation maximizes everything and is Pareto efficient, we must have equality here. It's not true in general. We could have combinations of constraints, but here we are in a special case where at every link there is a free variable. So we must have equality in the constraints everywhere here. So equality means x0 plus x1 is c, etc., which means that we have essentially all the, if I call x star the optimal value of x0, then we have this equalities everywhere. So I've transformed the problem in dimension 5 variables, which is embarrassing, something you can solve only numerically, into something which looks more like high school maths. We have to optimize something which has only one variable here. So we have to maximize log of x star plus, if I do the change of variables, each of the other rates is c minus x star. So that's the thing I have to maximize. And the constraint is this one here. So x star must be positive and the others as well. So those are the constraints. So that's, you study a function, you have a function of one variable, x star. You can compute the derivative, you find this, you can write the table of variations of this function, and you will find that there is a maximum at this value here, which is just equal to c over 5. Therefore, the proportionally fair allocation gives 1/5 of the capacity to the red and 4 times more to the blue, which was the intuition we wanted of proportionally fair allocation. The red is using 4 times more resources than the blue. The resources are exactly the same. There are links of capacity 1. They're all the same conditions. There's exactly 2 flows competing for every resources. So the axiomatic definition of, or what we want, at least from proportionally fair allocation, should lead to this, which is exactly what we obtain. So let's return to our second example, where we had known that the previous allocation here is not proportionally fair, if you remember. Now I'm giving you a hint. I'm saying that one of those allocations is the proportionally fair allocation. So I computed it. One of them is the proportionally fair allocation. Which one is it? I close the poll in a few seconds. Closing. And the majority says D, which is the only plausible answer. Why? Well, the first one we know it's not proportionally fair. We've analyzed this a few minutes ago. The second one is not Pareto efficient, because if we look at link 1, the constraint is 10, and we have a sum here that is less than 10. So I can always increase x1. I will get more, and the others don't move. So this is not even Pareto efficient. So it is certainly not the proportional fair allocation. Now, how about this one? Well, this one is deviating from the original by giving more to x0. And what we wanted by being proportionally fair is probably to give less to x0, because x0 is using 2 links instead of 1 like the others are here. So the only plausible one is D, which is the correct answer. But let's see how we can prove this. Well, we can do the same here. We see that this is a simple case where there is at least one free variable at every constraint. So the constraints must be binding. They must be satisfied with equality here, which gives, if I call x0 the main optimization variables, all the other variables must satisfy those equality, which leads us to maximizing this function. The problem is a bit different, but you compute the derivative and you find that the solution is 10/11. So this is the allocation we must obtain. We see that x0 will get this very small value here. x2 will get more, not much more than x0, but x1 will get considerably less here. So you see in the general case, it's harder to predict what the proportional allocation is doing. It's not 4 times more to this one than to this one, because here the situation is more complex. There are 2 links that are the same, but they are in different situations. Here the competition conditions are different. But we have one proportionally fair allocation, and in some sense, that's the one that makes more sense from the global management of your network here. In fact, we can interpret proportional fairness as what is called a utility fairness, because we have seen that proportional fairness, which has been defined axiomatically by saying, if we deviate from it, the total rate of change must be negative, so we cannot do better in that sense. That's the axiomatic definition. But we have seen also that it is maximizing the log of the rate. So the log of the rate, we can view it as a utility function. And there is a whole theory of utility optimization that says that, the theory of economy, basic models of economy are assuming that rational economic agents are maximizing the utility minus the price they pay. So the concept of utility comes from economy here. So we see that proportional fairness corresponds to utility, which is the logarithm of the rate. The logarithm of the rate captures well this proportional impact, which is if I have a rate of 1 and my rate becomes 1 plus 1, that is 2, then the utility has gone from log 1, which is 0, to log 2. So I've increased by log 2. Now, if I have a rate of 100 and I increase to 1, my utility goes from log 100, which is, if it's decimal log, it's 2, to 100, log 101, which is 2, log 0, 0, something, a very small increment added to 2. So the increase in utility by adding one amount of rate to the source is decreasing the value of x. It's called diminishing returns. If you have a large value, by incrementing it, the incremental utility is small, which is also saying that the utility function is concave. It increases, its derivative decreases. Its derivative says by how much the utility increases when you increment the value by a small epsilon, then this thing decreases, diminishing returns. This is exactly captured by this thing here. Now let's say proportional fairness and max-min fairness. The bad news is that max-min fairness cannot be cast as a global utility because the way it's formulated, you can always find cases where it doesn't correspond to global utility, to utility maximization, but almost. There is a result that says that if m is very large, and if we consider a utility function which is like this, for example, this one, 1 minus 1 over x to the power m. So if m is very large, that gives something that's almost flat for large values, goes to minus infinity and 0, and increases very steeply here. It's almost like a minus Dirac at 0 and a constant after that. Now, if you consider the utility, if you allocate rates in order to optimize this utility, the red one, the proportional fairness one here, you obtain something which doesn't have a name. It's a form of utility fairness, but for m very large, it converges to the max-min fairness. So we can think of the max-min fairness as a limit of utility maximization, where the concave function is very weird. It's like almost flat here. So something to remember, because that will tell us also what happens in reality in the internet when we look at concrete things, what is done in the internet. So, as far as at this point, we have seen that the most important message is that if we let sources run freely, then we are taking the risk of, one, inefficiencies, and in the worst case, if there are cyclic dependencies, congestion collapse here. So we need something which is called congestion control in the internet to control the rates of sources such that we use the internet resources efficiently and, in some sense, as fair as possible here. So a rate adaptation mechanism, which is what we will see now, should target some form of fairness. And we have seen two notions here. So, but ideally, perhaps we should target something that is close to proportional fairness. So that's the theory, at least the first part of the theory. In general, if I have a complex systems, how should I allocate rates? Now, how can we do it in practice? Well, everything that I'm giving in this slide exists somewhere in the internet. We can do what is called explicit rate base here. So a simple way to allocate the rates is to say to every source what is the maximum rate at which it can send, which is more or less what would be the logical consequence of all the little exercises we've done. We look at the scenario, we see, oh, this source should have 4C/5, that one should have C/5, and then we instruct the sources to have this maximum rate. This is what is done in cellular networks. When you share the access to Swisscom, for example, then over the link between you and the base station will have a rate allocation, which is trying to maximize the log, which is trying to follow proportional fairness here. Other mechanisms exist also, for example, in some data center mechanisms. It's called either hop by hop or fair queuing per flow. So those are two different mechanisms that are essentially built in the gigabits switches. Back pressure simply consists in once in a while sending a message back to the source to say, stop now. This is what TCP does when it sends a window equal to 0, for example. It's not very smart, but this is something that can protect a buffer. If, for example, in a switch, a buffer is congested, so it sends a signal upstream to say to all sources, please stop for a few milliseconds. So some gigabit LAN switches do that kind of thing. And of course, you must not just send stop, but the stop should die after some milliseconds, or you should be able to supersede it with a go signal here. There are other mechanisms that we'll discuss a bit later next week. And then there is what is done in the internet, which is end-to-end. All the other mechanisms are specific to some portions of the network. What is done in the internet is end-to-end by, what this means is that the hosts control the rate. How do they do it? They taste the water. That's an image. By trying to see whether there is something bad in the network and increase or decrease the sending rate using what is called the host congestion control algorithm. That's exactly how things work in the internet. In order to look at and see how it works, let's look at the simplest congestion control algorithm, which is deployed universally everywhere with one exception, TCP/BBR version 1, which is something we'll discuss next week. AIMD, additive increase multiplicative decrease. So it's like the credo of congestion control of the internet. It was implemented in DECnet, which was the network of the company that since disappeared, the digital company that built the first sophisticated network. You remember in the middle of the 80s, the internet was collapsing. In parallel, there were commercial networks, IBM, digital, etc. Those were not collapsing because they had congestion control. They were a bit more constraints. Of course, if you sell for huge amounts of money, a few kilobits per second to companies, and then it collapses because you didn't think that it could collapse, of course, that doesn't work in a commercial world. It worked in the internet, but it did not work in the commercial world. So the very beginning of the internet was not very attractive. The companies that had IBM SNA or digital DECnet had much better performance on those networking systems than over TCP/IP. Until TCP/IP adopted the solution, which is essentially the solution of DECnet, which I will explain here. It's based on this very simple analysis I'm showing here, where we model the network as a single bottleneck here. We will see how we can analyze more general networks a bit later. And the idea of end-to-end congestion control of the DECnet control, which is called the DEC bit, is to send feedback to the sources in the form of a single bit, so binary feedback, which is essentially saying, go ahead, a bit like the stop-and-go protocol, but it's not a stop-and-go, it is simply a positive or negative signal. If it's positive, you can increase. If it's negative, you should decrease. That's the idea of this mechanism here. And in this simple network model, the binary thing means if we are below capacity, so if the sum of the rates here, somehow if we have a mechanism, a way to detect it that is below capacity, then we send nothing, or which means positive feedback. If we're above capacity, we send a negative feedback. So we send a bit saying, hey, there is a problem, you should decrease. And then the sources are expected to reduce their rate when they receive negative feedback, and otherwise they can increase. Of course, they will not increase forever. They increase until their own capacity is reached here. Voila, that's the framework. We'll do a break now, and after the break, we will see how this led to the control systems that we have in the internet today. This is the sequence that leads to the control of the internet primarily. The question that comes is, so we understand now that we will have a local control that reacts to feedback by increasing or decreasing, and what increase or decrease law should we use? Now, if we want to do things simple, then we use linear laws. So at this time here, the idea was to explore the set of controls that have this form. I have a rate here at time t. Time is discrete to simplify. One is one time unit, so one round trip if you want, for this system. When I receive a feedback at time t plus 1, I transform the previous rate by using this affine formula here, which means I add something and I multiply the rate by something else. So there is a multiplicative factor and an additive term here. Of course, if we receive negative feedback, which is meaning here the bit is set here, this should decrease. So we will accept only multiplicative factors that are less than or equal to 1 and additive terms that are negative or 0 here. And same for the increase here. So that leaves us with the control of this form. Here's an example where that's a MATLAB style of a Python simulation of 3 sources that are sharing a bottleneck link with those parameters. U1 is 0.5, V1 is 0. That means when we receive negative feedback, we divide the rate by 2, we multiply it by 0.5, and the additive part is 0. And when we receive positive feedback or 0 bit, then U1 is 1. That means the new rate becomes the old rate plus 1 megabit per second. So we have an additive term, and we multiply by 1 means we do not multiply. So we are doing here what is called multiplicative decrease and additive increase. Here I'm showing on the y-axis the rate of a source, on the x-axis the time. I have source 1, source 2, and we see that they oscillate a lot because this system by nature is oscillating. We increase the rates until we go too far, then we are forced to decrease, and always increase again until we go too far. It's like bad kids, right? Until you have to constantly say, don't do this, they never learn here. So this is not learning in something. And we see that source 1 starts from this initial value, which is a small value, and the link capacity is 10 here. And source 2 starts from a high value, so we have initial conditions that are very different here. And we see that source 1 increases. Now, the sum of the rate of source 1 and source 2, which is even bigger, goes above capacity, so they receive negative feedback, which gives these oscillations. But we see that if we look at the first half of the figure, source 1 and source 2 converge to something that is oscillating, but it is around 5, which is half of the capacity. It's not extremely efficient because we increase or decrease by 0.5, but it is roughly efficient in the sense that it manages to shift the bottleneck capacity, which was 10 units of bandwidth, 10 megabits per second, with values that are in average the same for the two, even though they started from very different initial conditions. We can also observe what happens to a third source that started later, after those two guys have agreed to share the link fairly. We see that in long term, they share it fairly. So source 3 was 0 from time 0 to 100. And when it starts, then it will also have these oscillations. And these oscillations result in source 2 also decreasing here. They sense indirectly that source 3 is now active, and they are forced to decrease here. So this seems to work. We see that the total link capacity oscillates around the limit, and we see that this provides fairness, at least in the single case, a single bottleneck. Both notions of fairness we have are the same. They should have 1/3 of the link capacity, which is what is obtained here. Now the question is, could we do better than this one in this category of affine schemes or linear schemes here? So the first thing to do is to reason qualitatively about what we should do about those factors here. And one way to do it is to illustrate what happens when we have only two sources. When there are more than two, it becomes hard to draw a picture. But here, when I have only two sources, I'm depicting on the x-axis the rate of source 1, and the y-axis the rate of source 2. And the vector here represents where we are. That's the vector of allocation at a given point in time. I take a snapshot. I am here. Then we see that with such a scheme, we will increase both sources until we reach the capacity. So the capacity is given by the condition here, x1 plus x2 less than c, which gives this line parallel to the second diagonal here. So this scheme will have the effect that we will increase until we go above the boundary here, and then we will go back to the inside. So that's, in some sense, how far we are from this line is telling us how far we are from Pareto efficiency. We want to be Pareto efficient, so we want ideally to be on the line. And fairness is given here by the angle between the diagonal here, because in this simple case, if the only constraints are this, x1 plus x2 less than c, max min and proportional fairness, for max min it's easy to see, it will give the same rate to 1 and 2. And proportional fairness will also do the same because the constraints are symmetric in 1 and 2. If I maximize the sum of the logarithms, I will have at the optimum the same value for x1 and x2, which means that this is the target. We should be fair, means here we are on the diagonal, and if we want to be fair and Pareto efficient, we should be here. So the goal of such a scheme is to learn us through these variations that we do towards this point here. To understand what we should do, let's analyze what happens in this specific case here. I'm proposing to two sources. What happens if I do additive increase or multiplicative decrease? So here, the move 1 is a move here. Does it correspond to additive increase or to multiplicative increase or to nothing? And same question for move 2. Closing the poll in a few seconds. Closing. And the majority says A, which is the correct answer. Because if I do a negative increase, I add the same amounts to both coordinates, which means I do a move that's parallel to the diagonal here. If I do a multiplicative increase, I multiply the vector by a constant number, which means I am aligned with 0 here, which is the move number 2. Well, it tells us a lot of things. If we combine all the positive moves, if we look at all the positive moves, that's the one we've seen, multiplicative increase and additive increase, that's what they do. Additive decrease, that's what it does, and multiplicative decrease is shown here. Now, what we would like to do, so remember, we are starting here, probably things are random, we're trying to get there, and we're like a robot that tries to get there, but the situations keep changing. Which moves should we do? When we have to increase, the green and the blue both give us closer to Pareto efficiency, but the green does not bring us closer to this point. In particular, it doesn't make us closer to fairness. Right? So the green move here doesn't make fairness worse. We were at this angle, we are at the same angle, but it doesn't improve it either. When we decrease, then the multiplicative decrease does not make fairness worse, it does not improve it either, but the red increase, the additive increase, makes fairness worse here. So that's capturing all the effects. If we have to increase, then which increase should we do? Well, we should do a purely additive increase because that will bring us closer to efficiency, but also improve fairness. And if we have to decrease, then we should never have any additive decrease component. We should do only multiplicative decrease. Fairness will be improved only in the additive phase, and in the decrease phase, we should limit the problem by doing a multiplicative decrease. Therefore, if you use a scheme of that nature, the only reasonable thing to do is to decrease multiplicatively and increase additively here. So this is why we do this in the internet. If we use such a simplistic scheme, decrease or increase based on feedback here, the increase should be additive and the decrease should be multiplicative here. So this celebrated AIMD is what is implemented in the internet. In fact, the first response of Dan Jason and Sally Floyd after the first collapse of the internet was to implement this scheme here in TCP. We have a increase multiplicative decrease in a toy network example where the network was a single bottleneck. But we have seen that in reality, networks are more complex, which leads to multiple definitions of fairness. So if I do this, if I do AIMD on a single bottleneck, at least as a hand-waving argument, we can see that those oscillations will tend to move us towards the ideal point. So it provides fairness, which are both backspin and proportional. In a network setting, what should we expect to happen? Closing the poll in a few seconds. Closing. The majority says max min, but it's not a strong majority. Well, of course, that's not an easy thing, and it has taken many years for the academic community to find a solution to this answer. But this solution is now known. in reality, what it does, AIMD, at least with, if we assume that the additive increase is the same for everyone, and the multiplicative decrease is some component eta here, it leads to a utility maximization given by this formula. So this is based on the papers that you can find here. I did a summary of findings that goes beyond those slides, which is available on the Moodle of the course here in this document. So the proof of this uses approximation by solution of ordinary differential equations. So it goes way beyond what we want to do in this course. But the interesting thing for us is to tell us what it gives in practice. Well, I'm plotting here the logarithm function, which we know is what proportional fairness considers as utility function. And I'm plotting also this function for some values. Now, it depends on the value. Eta is always 0.5, but the increase, in fact, depends on the round-trip time and the packet size. So it's not as simple, but if I take those numbers here, this is the curve I obtain here for AIMD. So if we look at it from far, well, it's not very far from proportional fairness. So the first take-home message is, in reality, it's very close to proportional fairness. Not exactly, but it's a utility function, which means, and the utility that is concave here. So it will have this diminishing returns effect. So it should have something that would qualitatively behave similarly to proportional fairness. And if we want to be more accurate, we'll see that the deviation from proportional fairness is more towards this limiting case that we have seen. We can interpret max-min as the limit of utility function when we have a utility that's completely degenerate, which is minus infinity at 0 and everywhere. We see that goes more in this direction. So the take-home message is, well, it should do something that is closer, looks like proportional fairness with a small plus that goes into the direction of max-min fairness. That's for AIMD alone. In the internet, we'll see there is AIMD with additional mechanisms that change a bit the story. In particular, in the internet, the increase here is not the same for all sources, so that tends to blur a bit the picture, but as a first approximation, that's what we can remember. So that's a for the theory. We will see how this is implemented in TCP. But the theory, which is very beautiful and gives us a set of well-understood theories, max-min fairness, proportional fairness, AIMD. But in reality, it doesn't work that well, so we need to complement it with additional bells and whistles, which should not surprise you. This is how the internet is. We have a few main ideas that make this, and then we do things in detail, and we need to add this and remove that, etc. Here's one of the things we need to modify to the theory that is called slow start. The problem of slow start is that if we do things on a small time scale, it's not as beautiful as what I've shown before. Here I'm showing the same diagrams as I've shown a few minutes ago with the three sources that are sharing a bottleneck with additive increase of 1 and multiplicative decrease by a factor of 0.5. By zooming now on what happens to two sources, so if you remember, we had seen that the three sources, they converge to the same value and have many oscillations, so it looked fine. Now, if we look over a small number of oscillations, we see that, in fact, the red source, which is the third source here, that is, or the red in source 1 in this example here, takes a large number of oscillations until it gets something that is close. Large means 4 or 5 here, to get something that's close to what the others have. Now, one oscillation, as we'll see, is typically several round-trip times here. So that means that if a TCP connection lasts for not so long, in fact, it will never get there. It will never have fair sharing here. This is shown here by plotting x versus y is the rate of one source versus the rate of the other source. Oh, sorry, the red is source 3, correct? So I'm plotting here at time 0, we start source 1 had a rate of 4, and source 3 a rate of 0, so we are here. then we see that those oscillations will lead to this. And the fairness is exactly where we want to be. This is the points that we target on the curve, that we see that it takes 4 or 5 iterations to even get close to this. Whether this is bad or not, well, if we had only long-lived flows, and essentially when we had computers that were doing huge transfers, perhaps it doesn't matter. But for not so long-lived flows, it matters. So this justifies the addition to the sets of bells and whistles that are incorporated in congestion control, the addition of what is called slow start. So in slow start, we do something which is not at all slow. So it's a misser. Slow start means we start like source 3 from 0, and we increase exponentially fast. It's called a slow start because the alternative would be to start. I mean, if we do a TCP connection before congestion control was seen as a problem and a solution to the congestion collapse problem, what will a TCP connection do? It will start at the size of the window given by the receive buffer. So it would start at the maximum speed that the source and the destination can sustain, which might be way above the link capacity of the bottleneck between source and destination. So by default, if there is no congestion control, we do a heads-up start, which is called a fast start. So compared to this is slow. This is a slow start. But compared to a long window, it's fast because we increase the window exponentially fast here. So the slow start idea is we increase the rate multiplicatively until we have what we target. And if we receive negative feedback, we reduce the rate multiplicatively by a factor of half. Here we multiply by 2. We divide also by a factor of 2. But also when we have a negative feedback, we also modify the target rate to half of the rate that we have reached here. So we apply multiplicative decrease. That's a survival, it's a component of AIMD. We apply a multiplicative decrease to the rate that we had achieved here. So if I illustrate the rate of a source here, it increases exponentially fast. At this point, it receives negative feedback. So the target rate was 10 here, but it has received negative feedback, so it will decrease again. But when it decreases, the target rate becomes half of what it had here, which was 5 or something here. So 2 dot something becomes the negative rate. The intuition is here that when we were increasing, this rate here was quasi-feasible. We were probably not too much above capacity. So we try to target half of this rate here. This is slow start here. That's the algorithm. And this is, if I take exactly the same figure as before here, then when my source 3 is starting, we see that in essentially one iteration, in 2 iterations, it gets close to the point where the other sources were happening. Of course, the increase is unfair, and if we had only slow start as control mechanism, that would not work. That would, we've seen we need AIMD. So of course, we must exit slow start as we here reach that region, which is when we reach that capacity here. So this is what will happen with those 3 sources. And if you compare to what we had without slow start, we have 2 sources, green and blue, that were oscillating. They're doing AIMD. Now, when a source starts in the internet, we will not do AIMD. We will do slow start until end of slow start is reached. End of slow start is whenever we've reached half of the previous rate that forced us when we had received a negative feedback. And we see that it has the effect of very quickly joining the bands and oscillating at the same rate as the others are doing here. So this is the effect of slow start. And that concludes at least the first part, the theory part of congestion control. So congestion control is necessary, otherwise your internet will not work. A congestion control scheme aims at allocating rates according to some form of fairness. And if we include in fairness Pareto efficiency, like proportional fairness or any utility fairness or max-min fairness. And in the internet, the two ingredients that we have are essentially AIMD and slow start, plus zillions of other refinements that we will now discuss. So while the new presentation is starting, are there any questions on the theory we've seen so far? So let's continue on the congestion control. So we had a nice picture of bicycles and cars in the previous one. That's the theory. Now when we do it in software, in TCP, the picture is more chaotic and blurred. And this is exactly how things are. Still, the theory helps us understand why all the elements that exist are the way they are. And this will considerably simplify our understanding. The first thing, which is not at all obvious, is that congestion control on the internet is implemented with TCP. After all, TCP is a transport protocol. What is a transport protocol? Well, it's something that helps providing a good service to programmers, essentially to repair losses and doing flow control, which means making sure we don't flood a receiver when its buffer is full. That's what TCP is about. Congestion control, so there's a difference between flow control and congestion control. Congestion control is about providing inefficiencies in the network. So it's a network control function. It should be in the network layer if you're a purist of the dogma of layers. But it isn't. Why isn't it? Well, because when the congestion collapsed in the internet, people needed to do something very quickly, and they did not introduce in ICMP, for example, the internet, which is the protocol for internet control, they did not introduce messages to control the rate. Whereas such messages have been introduced. It's called source quench. Source quench exists in ICMP. It could be used, but it failed. It never worked for lots of reasons, but mainly because, remember, the internet is built on the idea that we have routers that are doing real-time functions, which consist in forwarding packets. So routers should not do complicated things like compute a max-min fair rate and update the value of the max-min fair rate and send it to every sources. So we don't want this to happen. So that's one of the motivation to do it end-to-end, to do it at the sources. And the natural place where something complicated is happening at the source is TCP. So that was pragmatic. So TCP will return a variable to adjust its window to the congestion status of the link between, of the path between the source and the destination, which we will see in a second here. Now, what is the negative feedback? Well, this is losses, packet losses. That was the decision that was done in the 80s here, which is a fairly bad decision that we have to live with it, because at those times, Wi-Fi did not exist. The network was Ethernet and telephone modems. That was the Ethernet when this was done. And losses, most losses were congestion losses, because you had smarter coding people before you had smarter networking people. So coding was well done on we had information theory done in the 40s. And so we know how to code on the modem link such that we don't stupidly lose packets because of noise on the line here. So the major reasons for losing packets was at that time buffer overflow, is still today primary buffer overflow, but today we have a lot of mobile devices. And the major reason for losing packets is the change in the mobile channel, right? I'm moving the channel condition between me and this base station is changing. And the more I go into 5G, 6G technologies that use lower range distances with higher bandwidth, higher frequencies, much tens or 100 gigahertz. It's very important to be well aligned, to be well in range, etc. So mobility creates packet losses. With mobility taken care of, nothing was mobile at those time. Right? A mobile computer would be a 40-ton trucks, right? So that was That was not an issue. But that's how it is. We will see how this is mitigated by what is called ECN. That will be next week. So TCP sources, they send packets. When they see losses, well, they conclude that there is a buffer overflow somewhere, which they interpret as a congestion loss. And the buffer overflow is on the routers or the bridges, not in the destination, because we have the congestion, the window mechanism of TCP that prevents that, and the sliding window that prevents that from happening. So it was not such a bad idea. Of course, I've asked questions, how about UDP? So the assumption that is done here is that most traffic is TCP, which is largely true. I mean, video streaming is over TCP. Still, when you do fast interactive video, you might want to use UDP because of TCP has this head-of-the-line blocking problem that we had, that we mentioned. So there are still some UDP sources that may generate a large amount of traffic. And the dogma today is that the UDP sources should imitate TCP. They should be TCP friendly. We'll talk about that a bit later. But you don't imitate TCP if you send a UDP query to a DNS server to resolve a DNS name, because you send one query and expect one reply. So the feedback mechanism that needs several iterations to happen doesn't make any sense here. So for small one-shot interactions, we don't do that. Now we will see that most traffic in Google, for example, is not using TCP, but is using QUIC. And QUIC runs over UDP. So of course, QUIC will need to be also TCP friendly. In fact, we will see that QUIC implements exactly the same congestion control mechanisms of TCP. There are multiple versions of it, and there are multiple, for every version of TCP congestion control, there's one version of QUIC that does the same thing. So we will focus here on TCP. The bad news is that there's plenty of things that have been done, but the good news is that they're all variants, with the exception of TCP-BBR, that doesn't work well anyhow. So they're all variant of TCP-Reno. So TCP is software, so it's easy to modify. Anybody can modify it. Anybody who can program in C++, for example, or in Go or whatever framework those things are done. So there are probably literally more than hundreds of versions of TCP congestion control, but those are the main ones, and those are the ones that we will discuss here. And the historical one, which is still present in most implementations, is called TCP-Reno with SAC. It's also called New Reno. So this is the one we will start describing today. The first thing is that then we introduce another, inside the code of TCP, we introduce another variable, which is called the congestion window. So congestion window is because, if you remember, one of the quiz we did when we talk of TCP is we asked if I have a slide W, and I have a round trip time of RTT, what is the maximum rate that I can have? And the answer was W divided by RTT, which was one way to address the question, how large my window should be to be efficient. But we can take it the other way around. If I want to control the rate, I can control the window. If I want to reduce, divide by 2 the rate of a source, then I can divide its window by 2. This is exactly the idea that underlines this. It is saying, we will control a window that is used by TCP. Of course, this window in principle is what is obtained in the acknowledgement packets by the window field in the TCP header. I call the value of this the offered window. We have seen ample details when we discussed the transport layer. Now, the true usable window is the minimum of this and another counter, which is called congestion window. And the congestion window is what is controlled during AIMD, additive increase, multiplicative decrease. Which means when I receive a loss, I have a negative feedback, I decrease the window, the value of the congestion window by 0.5. And when I receive messages positively, I have positive feedback, I increase it by a rate, which is essentially equal to 1 MSS per round trip time here. So that is, at least roughly speaking, how it works. There's a small problem in saying that because in the analysis we did, I spoke of rates, but this version of TCP doesn't control the rate. It just controls the window. There's no rate control. The only thing that is done is, can I send this packet? Is it inside the usable window or not? If it is sendable inside the usable window, I will send it. And if there are 10 packets that can be sent in the usable window, I will send the 10 packets, which might cause a burst of 10 packets. So there is no rate control in the sense that we space the packets to, if we take this as a definition of rate. So we need to lock this theoretical model that leads to AIMD, additive increase, multiplicative decrease, but is in the world of rates. We need to map this to the world of the window, of the sliding window. And this is what is done by the details of TCP Reno here. I mentioned also slow start. TCP Reno, like all versions of TCP, starts at slow start, which means when the connection is open, the value window is given by slow start. And we also get to slow start when a loss is detected by timeout. So we need to discuss this. When the loss is detected by timeout, we react differently than if a loss is detected by fast retransmit, which we expect fast retransmit to be the most frequent way of detecting a loss because loss detection by timeout is very inefficient. But it's not guaranteed to be the only case. We've discussed that when we discussed the details of TCP. Why is it so? Well, this is based on the heuristic or the dogma that whenever there's a timeout, it's not something normal. It's something bad has happened. All of this is based on heuristics. So heuristics, you imply them because you don't know, you don't have anything better, but you don't trust them entirely either. So if there is a timeout, that is interpreted by saying there was perhaps a loss that is due to something very bad, like a change, a major change in the network, perhaps a rerouting. So something that makes the situation non-stationary, an abrupt change. If there is an abrupt change, then we do like if the connection started. And so we go into slow start. That's the belief that's behind it. Otherwise, we do fast recovery, which is an approximation of the additive increase. We do additive increase, or multiplicative decrease. When we lose a packet, we should do multiplicative decrease and not get into slow start. Going into slow start means we set the window to the smallest possible 1 or 2 packets, right? Quasi to 0, and then we increase exponentially fast, which is way worse than doing a multiplicative decrease by 0.5. So how is IMD implemented? Well, the multiplicative decrease, sorry, not AIMD, how is, this is multiplicative decrease, yes, AIMD is multiplicative decrease and additive increase. So multiplicative decrease is implemented by a factor of 0.5. However, we don't abruptly modify the congestion window, or the window itself, but we modify what I could call a target window, which is in TCP code, is called slow start threshold, which is a completely ununderstandable concept if you don't follow all the details of the history of how the code went there. So think of it as a target window here, which is, for some reason, is not here. Additive increase is not implemented exactly, at least in most versions of TCP, is implemented by this heuristic, which is given here, for every acknowledgement or true acknowledgement of the ACK bit, of the ACK field in the TCP header, not a selective acknowledgement. So an acknowledgement that, remember that in TCP, when we send a new value of the acknowledgement, that means we acknowledge everything up to that value here. If there is a gap and some packets are missing, but I have other packets that were not missing, I send a selective acknowledgement. Here we're talking of the acknowledgement, not selective acknowledgement. Whenever I receive a new packet that advances the acknowledgement field, that is what it means by a new ACK is received, we increment the window by this value here, MSS. MSS is the maximum segment size, the size that is used by TCP. Remember that TCP will try to avoid fragmentation, so needs to give a guess on what is the packet size, and that is negotiated at the beginning of a TCP connection, typically in the first same packet. So this given by this value, which seems like a weird value, but remember, because the congestion window is counted in, like everything in TCP, is counted in bytes, not in packets. If I translate this formula into packets, so assuming packets of size MSS, which we can do, of course, TCP is free to have packets that are larger or smaller, but as a thought exercise, assume everything is counted in packets of size MSS. I change the units, so I need to divide the value of CW&D by MSS, then that will give this. Whenever we receive a positive ACT, we increment by 1 over congestion window divided by packet. So if your window is 10, whenever you receive a new packet, you increment by 1 over 10, which is a computer science view of if I do it 10 times, I increment by 1, right? Which is not exactly true, but more or less true, which is illustrated here. The idea behind that is we want increments do an additive increase, roughly speaking, once per round trip, not for every acknowledgement received. So this is the difference between a rate control protocol with a rate supervisor that does everything, like we could do as a thought experiment in the exercise we saw before, and the reality, which is this TCP finite state machine at the source that sees ACKs, losses, and has the size of the window. Here's an example where I send one packet, I get an acknowledgement. So the congestion window started with 1, then the new value will be 2. But now if I start with a window of 2, we see that in order to, for every packet that I receive, I incremented by 1 over 2 for the first one, and 1 over 2.5 for the second one. Now, many TCP implementations do exactly this. TCP new Reno implementation do this. Some other TCP new Reno implementation do something a bit different. They don't update the window immediately, particularly if you receive several documents within a short time. You might do this in block, 1 over the state of the congestion window before you receive the 2, which is, if you did this, you would increment by 0.5 again, and you reach the value of 3 instead of 2.9. So, but if we do strictly what is said here, we have something which is a bit less than additive increase. It's here within one window, we increase by 0.9 instead of 1. And here, the next window, we increase also by about 0.9. It's a bit less than additive increase for 2 reasons, because if you do 1 over x n times in a x times, you don't increment by 1, but something that's a bit smaller. And also because you don't increment by 1 MSS every round trip time exactly, because what is called a round trip time here is the time to receive acknowledgements for the full window, not for one packet. Here it takes the time to send and acknowledge the 2 packets. So the larger the window, the longer it is to have all this fully acknowledged. So the time also is incremented, which means the rate is less than a constant per MSS, but this is how the creators of TCP Reno did it. So take-home message is we do a slightly sublinear increase, which is a sub-approximation of additive increase. But the good thing is we don't need any network controller that sends messages to the source. It's just as the source receives acknowledgement, it's done for free. That really explains why things are this way. When the internet was done, the routers were built, and there was no way to change it. And even if we would like to change it, probably we'd have to build routers that would have such a complexity that we would not like to do it. The networks like IBM SMA were not at all doing this. So the IBM routers were effectively computing rates and sending information to sources. But this did not survive. Right? The only thing that survived is the IP routers at the end. So we've seen AR&D. Now, when you do slow start, we need to do multiplicative increase. And multiplicative increase is implemented in a very similar way, having this formula here that says whenever I receive a new acknowledgement, I increase by one packet, which has this effect here. If I start with a value of 1, then when I receive a packet, an acknowledgement, my window becomes 2. I send 2 packets. So when I receive the first pack, it becomes 3, then 4, which has effectively the effect of doubling the window size whenever a full window is acknowledged here, which is a bit less than multiplicative increase because the time it takes is not constant, but not far from it. If we combine the two, we have typically a plot like this one. I'm showing on the x-axis time, the y-axis the window size, the congestion window, the user size for as controlled by TCP. We see that we start in slow start, so we raise the window exponentially. We must guess what is called the target window, which is called slow start threshold in TCP. Now we understand why the target window is called slow start threshold, because it is really the threshold that we put when we do slow start here. And then if we have a loss before hitting the target window, we know from slow start we restart with a target, which is half of the window we had reached. So the slow start threshold becomes half of this value here. So this is an example of slow start where you had to do slow start with 2 increases until I get here, which is not very typical. Most of the time, we reach the target window here, but that may happen. And then the window size increases as long as nothing bad happened, as long as we don't detect any loss. Then when I detect a loss, if the loss is detected by timeout, like it's showing here, then we go into slow start again with a target window, which is half the window that we had just before the loss here. Until we exit slow start. It can be like here, but here it's done in only 1 iteration, and etc. So this is how AIMD is implemented with this annoyance of slow start. But if you look at only the target window, the dotted line here, you have a clean, almost clean version of AIMD, and this is how the congestion window is managed in TCP. However, there is a problem. If you remember the formula, it says that it says that the time is over. So yes, I don't have enough time to cover this, so we will do it next week.